So we are now on chapter 16, Forecasts and Fudge Factors, Modeling Expectation Formation. Expectations are fundamentals to decision making. Modelers must portray the way the agents represented in their models form forecasts and update expectations. These models must be consistent with the principle of model formulation developed in early chapters and must be grounded in empirical study in the field. This chapter develops a boundedly rational formulation for modeling forecasting and expectation formation, particularly for situations where the variable of interest is growing. Examples used to test the model include forecasts of inflation, commodity prices, and energy consumption. In this chapter, we will tackle the modeling expectation formation and a sample case study about energy consumption, commodity prices, and inflation. Also, we have implications for forecast consumers. Then initialization and steady-state response of the trend function. And lastly, we have the summary of this chapter. Modeling expectation formation. All decisions depend on our mental model of the situation. Expectations about the future of the system form a critical component of these mental models. We constantly form expectations about what is likely to happen, and these expectations guide our actions. Models of forecasting process must capture the way people form expectations and should answer the following questions. Are forecasts prepared judgmentally or with formal techniques? Second, are the formal tools simple or complex? The model must capture the cues used in the forecasting process and the way in which the cues are combined to yield the forecast. Realistic models must also capture the social and political forces that influence an organization's forecasts and decision making. For example, an organization may use a large econometric model with hundreds of variables to forecast the economic environment. But if senior managers ignore the model's output and go with their gut feelings, then your model of the forecasting process can't assume the sophistication of the large-scale model. Instead, you must capture the ways in which the manager's intuitive judgments are formed. That is, how they consume and the way they digest it will lead to that certain feeling in their gut. The social and political nature of forecasting means many judgmental heuristics and other manifestations of bounded rationality may have considerable influence on the forecasting process and can lead to persistent, systematic forecasting errors. Expectations are usually modeled in system dynamics as adaptive learning process such as exponential smoothing. Adaptive expectations are common in economic models as well. Adaptive expectations outperform many other forecasting methods over longer time horizons. Sometimes expectations respond not just to the history of the variable, but to its past values and past trend in orders may be used to estimate like future order rate. Exponential smoothing does work well for trends. The output always lags behind the input, causing a steady-state error whenever the input is steadily growing. Steady-state error means the output never equals the input even after sufficient time for transient adjustment has passed. Figure 16-1 shows that forecasting challenge hypothetical forecasts of a variable. Measurement and reporting delays mean the actual current value of the variable to be projected is unknown, introducing error. The length of the historical time horizon used to estimate the trend in the input dramatically affects the forecast. Modeling expectation, the trend function. According to John David Sterman, the J. W. Forrester Professor of Management and the current director of the MIT System Dynamics Group at the MIT Sloan School of Management, growth expectations in system dynamics are often modeled with the trend function. The input to the trend function can be any variable. The output is an estimate of the fractional growth rate in the variable, but trend is not just a clever way to calculate growth rates. As the input to decision roles in models, trend represents a behavioral theory of how people form expectations and take into account the time required for people to collect and analyze data, the historic time horizon they use, and the time required to react to changes in the growth rate. The trend function generates the expected rate of change in the input variable, expressed as a fraction of the input variable per time unit. The trend function involves three parameters, each the time constant of a first-order exponential smoothing process, or TPPC, or time to perceived present condition, THRC, time horizon for reference condition, and TPT, which is time to perceived trend. Figure 16-2 shows the causal structure of the trend function. The output is an estimate of the fractional growth rate in the input variable. The structure has three parameters: the time to perceive the present state of the input, or TPPC. Second, the historical time horizon against which the perceived condition is compared, or THRC, and the time for beliefs about the trend to respond to change in its indicated value, TPT. Behavior of the trend function. The trend function has the desirable property that it provides, in the steady state, an unbiased estimate of the fractional growth rate of the input. If the input grows exponentially at rate g, the steady-state output of the trend function is also g. This portion will be discussed further at section 16.6. Next, the parameters of the trend function determine its transient response to changes in the growth rate. Figure 16-4 shows partial model tests illustrating for a range of parameters. It responds to a change in the growth rate of the input. The longer the time horizon for establishing the reference condition, or the longer the time required for decision makers to perceive the trend, the more gradual the response. Figure 16-4, Behavior of the trend function. The input, initially constant, begins to grow exponentially at 5% per year at time zero. The parameters are as indicated, with TPPC is equals to 0.25 years in all cases. Figure 16-5 Forecasts of U.S. total energy consumption in 1985. Each point represents a forecast of consumption in the year 1985, plotted in the year the forecast was made. Figure 16-6 shows the response of trend function with parameters estimated for energy forecasts. The input begins growing exponentially at 5% per year at time 0, while Figure 16-7 shows a simulated and actual forecasts of U.S. primary energy consumption in 1985. Figure 16-8 shows forecast and actual total electricity consumption in the U.S. Forecasts of the North American Electricity Reliability Council or NERC in the year 1974 to 1990. In such highly politicized environments, it is small wonder that many modelers cherish the free parameters, enabling them to adjust their forecast to match the expectation of their clients. Case study on commodity prices. Smoothing and trend extrapolation also explain forecasts of the prices of many commodities. As an example, Figure 16-9 shows the cash price of cattle in the U.S. from 1972 to 1986, a period of great price volatility. Also shown are the one-quarter ahead forecasts of Glenn Grimes, a professor of agricultural economics at the University of Missouri and a respected professional livestock market analyst. Figure 16-10 shows the correspondence between the simulated and actual forecasts. The model replicates Grimes' forecasts well. The mean absolute percent error is 4.5%, and the R2 of the model is 0.95. Because smoothing introduces a delay, the simulated forecasts, like the actual forecasts, miss major turning points in price because it takes time for the expectations about the trend to change. The model also captured the overshoot of the forecasts after the large price rise in the late 1970s when Grimes, like the trend function, predicted price increase to continue for a while even though actual price fell. Case study on inflation. Inflation expectations are critical to decisions throughout all sectors of the economy, including monetary policy, the pricing of stocks and bonds, capital investment, collective bargaining, projections of tax revenue and government expenditures, and your own investment decisions. The stakes are high and the task is daunting. Inflation is volatile and is affected by a host of economic events and variables. Consequently, inflation is one of the most intensively studied economic indicators. Figure 16-11 shows the Livingston Panel's inflation forecast compared to actual inflation. Figure 16-12 shows the trend function compared to the Livingston Panel's 6-month forecast. The parameters of the trend function are TPPC is equals to 2, THRC is equals to 12, and TPT is equals to 2 months. While figure 16-13 shows the simulated 6-month Livingstone forecasts fixed anchor model. Figure 16-4 shows the simulated Livingstone forecast say anchor model, and figure 16-15 shows the 6-month Livingstone forecast versus actual inflation in the year 1947 to 1997. The plotted values of actual inflation differ slightly compared to figure 16-11 due to revision in the CPI since 1985. And lastly, figure 16-16 Livingstone panels 6-month forecast compared to C anchor model in the year 1947 to 1997. Implications for forecast consumers. The results suggest important lessons for forecasters and especially for managers and decision makers who must choose which forecasts and forecasting methods to buy. First, most forecasts are not very good. Forecasts are most accurate when the underlying dynamics are stable, as when predicting the influence of regular phenomena such as seasonal variations. But forecasting methods are particularly poor when there are changes in trends, noise, and other sources of turbulence. These are precisely the times when people are most interested in forecasts. Second, most forecasting methods frequently miss changes rather in trends and turning points in cycles, lagging behind rather than anticipating them. The systematic errors in forecast of inflation, commodity prices, energy use, and other variables strongly suggest adaptive expectations and simple trend extrapolation often dominate professional forecasts. These methods do correct errors over time, but because they involve smoothing past data, they inevitably introduce delays that cause the forecasts to miss key turning points and shifts in growth rates. Third, smoothing and extrapolation of the past trend is the variable itself seems to dominate other consideration in forecasting. Though forecasters often claim examine a wide range of variables in making their forecasts, past values and past trends strongly anchor their forecasts. The influence of other variables is weak because their connections to the target variable are poorly understood, unstable, noisy, and ambiguous. Fourth, forecasters tend to underestimate uncertainty in their forecasts, often failing to provide a range, alternative scenarios, or a list of factors to which their forecasts are sensitive. So the challenge is here for extrapolation and stability. The expectation formation process can dramatically affect the stability and performance of the system. It takes time to build capacity. However, managers in growth markets must forecast the demand for their products far in advance. Forecasting too little growth leads to capacity shortages, eroding market share because you cannot sell more than you can make. Forecasting too much growth, on the other hand, leads to excess capacity, destroying profitability. Initialization and steady-state response of the trend function. To be reasonable model of growth expectation formation, trends should produce in the steady state an accurate or unbiased estimate of growth rate in the input variable, as it is shown in the formula. The proof relies on the fact that the steady-state response of first-order exponential smoothing to exponential growth is exponential growth at the same rate as the input but with steady-state error. When the input is growing but exponentially, the smoothed variable lags behind the input by a constant fraction of the smoothed value. In the trend function, PPC is a smooth of the input, so in the steady state of exponential growth rate g or period, PPC will also be growing exponentially at rate g, which is precisely the expression for the indicated I trend. So to summarize this chapter, forecast and expectations are fundamental to decision making. Theories of forecasting range from rational expectations, in which people are assumed to have nearly perfect understanding of complex systems and never make systematic errors, to theories in which behavior is simple and people never learn. Experimental and field studies support an intermediate theory in which rationality is bounded. Behavior and expectations do adapt, but slowly. We often learn the wrong lessons from experiences and frequently make systematic errors in forecasting and controlling complex systems. This chapter introduced and tested a boundedly rational formulation for modeling the formation of growth expectations, the trend function. The trend function models the way in which people form expectations about the rate of growth in a variable based on the history of the variable itself. The trend function was tested with several examples, including forecasts of inflation, commodity prices, and energy consumption. In all cases, the forecast can be modeled well by adaptive learning process such as exponential smoothing and trend extrapolation. Forecasters frequently miss turning points, overreact to trends, and generate other systematic errors. Learning is often quite slow relative to the dynamics of the variables people seek to forecast. Forecasts are often dominated by simple adaptation to past events, even though forecasters claim to consider a wide range of variables and use complicated models to generate their forecasts. The past history and trend in a variable act as a strong anchor on people's judgments and constrains the range of values they consider reasonable. In situations where the relationships among variables in the system are noisy, unstable, or obscure, the trend is the target variable will loom large in the forecasting process and dominate the effect of other predictors. Similarly, forecasters often adjust the inputs to their models until the outputs conform to their intuition and to social and political pressures. So that's the end for this chapter and for the group 4 reporting. We hope that we are able to impart some knowledge for these chapters we have for you, and thank you very much for your time. Once again, this is Shirley Yamamoto Ginano reporting.